something. So if you know, can you just recall what is semiconductor, or let's say what are metals? You can just try to remind and try to tell me something, so this way things will revise. What are the type of materials, or we have their division, like insulators, conductors and semiconductors? Any idea? Yes or no? Can you hear me?
Yes, germanium is a kind of semiconductor.
Okay. Yeah, these are examples. Silicon, which you are saying, these are examples. I'm asking the type of materials basically, or you call metals. So they are conductors, insulators, yeah, and semiconductors. Correct, Mariam? Yeah, yes. So what are their properties? How can we differentiate them? If you want to differentiate between conductors, insulators, and these, so how will you say this is called conductor? The properties, what are the properties of, let's say, conductor first?
Conductor has a high speed of like connecting electricity. It's
okay,
like faster.
Current can easily flow. Current can easily flow in conductor. They allow the flow of current, correct?
Yes.
Okay, all right. So, okay, what about the insulators then?
Current cannot flow.
Current can flow, all right. So, what's the examples of insulator? Some examples. Plastic. Correct. Plastic, rubber, wood, yeah. And for the conductors, rubber, yeah. Conductors,
iron.
Okay, iron, metals, gold, silver. These are all, very good conductors of electricity, basically. Now, yeah, FA or FE, I think, yeah, iron, I think. So, yes, and what about the semiconductors then? As the name, semi.
They have
So, semi, yani, whose properties lies between these things, like, yeah, conductors and insulator, right? This is something. All right, so I was just searching some videos for you so that I can show you. Just a minute, then I'll share you. All right, so what are the semiconductors? Semiconductors are basically the one whose properties lies between insulators and conductors. So they can work as a conductors, they can work as an insulator. These are called semiconductors. Let's see, I have some videos earlier, long time before. Maybe if I have, I can show you this one. Can you see the video?
Yes.
Look.
There is no sound.
Just there is no sound?
No.
How? Really? No sound. Okay. It should be. Maybe I am using the mic. It's like that. Again, I'm trying to see this one.
No, still no sound.
No sound. Okay, so then I'll do one thing. I'll copy this link there and you just watch it quickly. That will be also fine. Okay, you can make sound share from Zoom. Sound share. Okay, how is it like that? In the sharing option. Okay, share computer sound. Okay, Very good. New option. All right. Now see and tell me.
Here I have a circuit
All right.
with a battery, light bulb, and gap. If I fill this gap with a metal, the light comes on. If I fill this gap with glass, the light stays off. You probably already know this because metal is an electric conductor and glass is an insulator. But what happens when I fill this gap with a silicon wafer? The light stays off, so you might think the silicon's an insulator. But what if I heat it up? Thank you. It lights up. The silicon is insulating at room temperature, but conducts electricity when it's very hot. It's a semiconductor based on the environment. This special ability makes semiconductors the perfect brains for electronics, are at the heart of computer chips, and enable them to do math and run programs. Semiconductors have a... But what is it exactly about these semiconductors that allow them to either conduct or insulate? In a single atom, electrons can occupy specific energy levels. When multiple atoms bond, the electrons are shared between them. But because the atoms are now interacting, the energy levels shift around. In a solid, trillions and trillions of atoms interact with each other. Their individual energy levels smear into energy bands. For a material to conduct, the electrons must be able to jump from lower energy to higher ones. The spacing of these energy levels and how they're filled with electrons determines if the material is a conductor, insulator, or semiconductor. If there's a huge gap between the lower energy levels and the higher ones, it's hard for electrons to jump to the higher ones. So current can't flow, and it's an insulator like this glass. Metals have no gap at all. Electrons can move to the higher energy levels with no problem. Current can flow. Semiconductors fall somewhere in the middle. They have a medium-sized band gap. So technically, I can make this glass conduct electricity if I added enough energy through heat to push the electrons into a higher band. But that amount of heat would either melt or break the glass before it actually conducts. This is true of most insulators. The amount of energy needed to make them conduct is just too high. But in a semiconductor, the band gap is small enough that electrons can jump into the higher energy band so that current can flow. The amount of heat we apply determines how many electrons jump into the higher band and how much current flows. And heat isn't the only way to change the conductivity in a semiconductor. We can also use light, electric currents, and in a computer, electric fields. As I've said, computers are made up of semiconductor switches called transistors that switch between conducting and insulating. Computers use electric fields because heat is slow and would burn too much energy. We can turn this wafer into a computer chip by printing a circuit of transistors on it using a process called photolithography. Here, in the photo room, we cover the wafer with a light-sensitive material and expose it to light that we shine through a patterned mask. Then, we develop the wafer, like film and photography, which leaves behind a pattern that becomes the circuit. Printing the transistors at once lets you make circuits that are smaller and cheaper than if you built them from individual parts. Transistors make up the logic elements, the memory components, and the communication modules that let computers talk to. You can cheaply add transistors to almost any device you can think of, from spaceships to servers to maybe even your toaster. Semiconductors have enabled the technological revolution, the internet, the computer, and the cell phone. No semiconductors, no information age.
So, did you get the idea?
I'm Jamie.
Yes.
Yes.
So, no semiconductor, no technology. It's like that. So this is something. I'll share this link to you so that you can also check it, right? I just recall it because it's this video I found long time before. I used to share with the students, and then I just thought maybe I have, so that's why I was searching while I was talking to you. So then I find this video. All right, so this is something, yani, this is the importance of the semiconductor. You know, you people use memories in your mobile phone. You people use memory where here, yani, in mobile phone, in a flash drive, you people use, in computer we have a memory. So we have memory everywhere, but how it is made up of? It is made up of semiconductors basically. And you know, the electronic switches, it is again made up of semiconductor. What is electronic switches? Nowadays, maybe you are, you know, there's some smart, you know, Internet of Things, the very common word nowadays. Smart homes, very common words nowadays. Like, you will give command, yeah, please turn on this video, or turn on this lamp, my room lamp. It is happening because of, again, semiconductors are there. There are, you know, diode switches. They are basically diode can work as a switch which can turn it on, turn off the current flow to any particular device. So like smart homes, what we are having, we have an app. So we are anywhere in the world, we can just open that, and you know, it is connected to the internet, and we can turn on, turn off the appliances you know, of our home by just clicking on and off there. So how it is happening? We just use it. So there are transistors, there are diodes, those work for it. So they can work as a switch. So when a proper amount of biasing applied, so they can either conduct the current, and it can, like a closed switch, open switch. So we will discuss now what are a semiconductor, what is the diode, and how it is work, what is the construction of it. So it's all about. So yeah, so it's long time before I used to have this video. I will share all, I have other video also, those are very interesting. So I will share videos. Where are the others? There are some intrinsic semiconductor, extrinsic semiconductor, I think. Yeah, really, it is very, very interesting topic. Though I was thinking, you know, this should be basically, you know, more in detail rather than this just RC, this circuit and this circuit, because this is the technology nowadays. But see what we have. Yeah, these are the links also. So this is extrinsic semiconductor, working of PN junction diode, transistors and all. So I will share with you. Okay, now I can share. This is semiconductor. This is extrinsic semiconductor, which we will discuss now. Extrinsic. Then working of PN junction diode. Yeah, so this is the topic which we are going to discuss. These three now, one by one. So let's see this one, the second one. You can check later on. I just share it. So this is extrinsic semiconductor. Okay, before that I will introduce first. So guys, now we know that what is semiconductor. So basically semiconductor is just a minute. Let me share the. Okay, so semiconductors are classified into two categories. One is called intrinsic semiconductor. Another one is called extrinsic semiconductor. What is intrinsic semiconductor? Intrinsic semiconductor is basically a pure form of semiconductor, is called intrinsic semiconductor. All right. Now, so pure semiconductor, you know, in an outer shell, it has only 4 electrons. It means it can either give 4 and, you know, or take 4. So it means what happening here, in order to increase the number of holes, any positive charges, or number of electrons, we used to add some impurity to the pure semiconductor. Okay, so impurity, like we need to dope some impurity. So it could be 3 valence, you know, at what you call atoms of 3 valence type of material we add, or pentavalent, 5 valence, so that either if we add pentavalent, yani what will happen? Number of electrons will be more. If we add trivalent impurity, so more holes will be there. So this way we form extrinsic semiconductor. Yani extrinsic semiconductor is what basically pure semiconductor added with some impurity, some doping to the pure, we get the extrinsic semiconductor. So extrinsic semiconductors are now 2 types, either P type or N type. P type, yani it can, the charge carriers are there, holes. Okay, and N type charge carriers are basically there, electrons, yani more electrons are there. So now I believe it will be clear to you when you see this video also. So 5 minutes.
Extrinsic semiconductors. In intrinsic or pure semiconductor, concentration of both electrons and holes at normal temperatures are very low. Hence, to get appreciable current density through the semiconductor, a large electric field should be applied. This problem can overcome by adding suitable impurities into the intrinsic semiconductors. The extrinsic semiconductors are those in which impurities of large quantity are present. In general, the impurities can be either third group elements or fifth group elements. Based on the impurities present in the extrinsic semiconductors, they are classified into two categories. 1. N-type semiconductors and 2. P-type semiconductors. N-type semiconductors. In order for silicon crystal to conduct electricity, we need to introduce an impurity atom such as arsenic, antimony, or phosphorus into the crystalline structure. These atoms have 5 outer electrons in their outermost covalent bond to share with other atoms and are commonly called pentavalent impurities. This allows 4 of the 5 electrons to bond with its neighboring silicon atoms, leaving 1 free electron to move about when electrical voltage is applied. As each impurity atom donates 1 electron, pentavalent atoms are generally known as donors. Antimony, Sb, is frequently used as pentavalent additive, as it has 51 electrons arranged in 5 shells around the nucleus. The resulting semiconductor material has an excess of current-carrying electrons, each with a negative charge, and is therefore referred to as N-type material with the electrons called
So these are the
majority
majority
carriers.
carriers here. And what are the minority carriers? Holes, because they are very less. And now we have more electrons here. So that's why they are called majority carriers in the N-type semiconductor.
And the resultant holes, minority carriers. The block diagram of N-type impurity doping and corresponding band diagram is shown in figure 1. P-type semiconductors. In contrast to N-type of semiconductor, if we introduce trivalent 3-electron impurity into the crystal structure, such as aluminium, boron, or indium, only 3 valence electrons are available in the outermost covalent bond, meaning that the 4th bond cannot be formed. Therefore, a complete connection is not possible, giving the semiconductor material an abundance of positively charged carriers known as holes in the structure of the crystal. As there is a hole, an adjoining free electron is attached to it and will move into the hole to fill it. However, the electron filling the hole leaves another hole behind and is forth, giving the appearance that the holes are moving as a positive charge through the crystal structure, conventional current flow. As each impurity atom generates a hole, trivalent impurities are generally known as acceptors, as they are continually accepting extra electrons. Boron, B, is frequently used as trivalent additive as it has only 5 electrons arranged in 2 shells around the nucleus. Addition of boron causes conduction, which consists of many of positive charge carriers, results in a p-type material, and the positive holes are called majority carriers, while the free electrons are called minority carriers.
Yes, so did you get the idea? Complete idea? All right. So this is what basically n-type and p-type. Now, up to now, you have understand that we have a p-type semiconductor, how to form it, and we have n-type semiconductor. So the topic which is we are going to start, this is p-n junction diode. Yani we will be using p-type, we will be using n-type, and we will design an p-n junction diode. How it is gonna be? We need to join p and n-type together in order to form p-n junction. Okay, so this formation, or you can this is not like just we just add them together. So p-n junction diode is what? A p-n junction is a formed electrons in the n material. Okay, so how it is forming, again we have a video, see this one. So you will cover a lot of things by just looking to this video also. This is about p-n junction. Okay, just let it pass first. Okay, so here is guys what this video is. Can you hear the sound also? My computer, I think, yeah, I have shared right. All okay. So what I said, what is this video about? It's this video about we have p and n type both have a p-n junction diode. And how can we form it? We have a p-type, we have n-type, we are going to join them together. Joining is not like we have a glue and we just put it and we join. There is a different technique we call alloying technique, or something. So when we form this one, okay, up to now I think everyone is okay. This is p-type, so there will be a majority charge carrier will be holes, and for n-type majority charge carrier will be electrons, right? This is clear.
Yes, correct.
Also, do you know that different type of charges have attraction, and similar type of charges have repulsion, right? So what will happen, girls, when I bring this p and n type together? So electrons will start attracting towards the p type, and p type will start attracting towards this one. So what will happen? Yeah, attraction will be there. So let's see now. In the beginning, when I bring this p and n type together, so there will be attraction start, and they will combine here. When they will combine here with the electron with the holes, what will happen? It will form immobile ions. Rani, they will not move forward. So because of it, what happened? They will form a depletion region here. In that region, it will be filled with the immobile ions that cannot move. So they will create a potential barrier. Yani further diffusion, yani movement of electrons from n type to p type and holes from p type to n type will stop, because they will create a barrier here. That barrier is called junction or depletion layer. So you will see this video. Hope it will be clear to you.
Animation covers how a p-n junction semiconductor works, what is forward bias and reverse bias, what is diffusion current and drift current, and what is avalanche breakdown. What is p-n junction semiconductor and how is it formed? It is a combination of p-type semiconductor with n-type semiconductor to achieve the practical utility of both. It's formed when a p-type semiconductor is joined to a n-type semiconductor. Now with the help of this animation, let's see how the p-type semiconductor and n-type semiconductors work. So the p-type semiconductor has holes which are positively charged, and the n-type semiconductors have electrons which are negatively charged. So you can see free holes which are positively charged are available in the p-type, and free electrons which are negatively charged are available in the n-type. So this is the region where the p-type and the n-type joins, or the junction which is formed, which is called as the p-n junction. So this is the p-n junction. What happens when a p-n junction is made? Electrons near the junction jump from n-type semiconductor to the p-type semiconductor, and holes near the junction jump from the p-type semiconductor towards the n-type semiconductor. This phenomena creates a space charge region at the junction. So this is a space charge region which is created at the junction. Electrons are available in the p region at this space charge region, and holes are available in the n region at this space charge region. An electric field is also created in this space charge region because of the movement of these holes and the electrons, and the direction of the electric field is from the n-type region towards the p-type region. Some electrons move back from p to the n in this space charge region, and some holes move back from n to the p in this space charge region. So it moves back also, and this continues to happen till an equilibrium is reached at this region. This movement of electrons and holes in the space charge region gives rise to a current, and this current is called as diffusion current. Now let's see forward bias.
You don't need diffusion current and all these to understand. It's just like, electrons move here, so they create here, immobile ions, and here, so they will create a barrier over there. Any further electrons cannot go there and electrons cannot go there. So there is a gap created here. So in order to finish this gap, okay, and there's a potential barrier is created here, and this potential barrier is fixed for silicon. Do you remember the germanium also, another type of semiconductor?
Yes.
Germanium. All right. So this is 0.7 for the silicon potential barrier and 0.3 for the germanium. Means this potential barrier can be removed if we apply the voltage across P and N type in a way. Okay, that is, now we will look here how when we apply voltage here with the P type and N type, what is forward bias? Forward bias, if we apply, if we connect positive terminal of the battery with the P type, positive terminal, let's suppose I have a battery here which is positive, and I am connecting this positive to this P type. Okay, and I am connecting this negative terminal to negative type. So this is something, now if it should be at least 0.7, so that this the barrier which is created here, it will finish. So current and electrons can jump here, and current can pass through it. This is something. So this is forward bias and reverse bias, it's all about. So drift current, diffusion current, you don't need to go, we are not going to ask these things. But what is PN junction? It should be clear to you. Now, how it is formed, it should be clear to you. Now, what is forward bias and reverse bias? Yeah, this is very important. So long focus here.
In forward biasing, positive terminal of the battery is connected towards the P region of the PN junction, and the negative terminal of the battery is connected to the N region of this PN junction semiconductor. And you can see the positive terminal repels the holes in the P region, and the negative terminal repels the electrons towards the junction in the N region. So a pressure is acting.
So why it is happening, because of we connected this with the positive. So this is connected with the positive, right? This is connected with the positive because of the battery. So what will happen? We know that similar type of they have repulsion. This is positive, this is positive. So they will repel here. So because of this repulsion, there is a force applied to this depletion layer. So this depletion layer with applying voltage is gonna be removed. This is what he's trying.
Towards the junction, and this result in the junction to shrink. You can see the junction is shrinking there. Due to this repulsion, the depletion region or the space charge region narrows down, as you can see in the animation. If the voltage in the forward bias is
a
above
specified range,
specified
which I already
range,
told you, if it is made up of silicon, it should be at least 0.7. If it is made up of germanium, it should be 0.3 volts.
these electrons in the N region drifts through the junction and migrates to the P region and towards the N region as like this.
Now go to
The
the,
junction towards called
you
as
just leave
the
this one.
drift
Now reverse
current.
bias.
Now terminal of the battery. For reverse bias to achieve in PN junction semiconductor, the negative terminal of the battery will be connected towards the P-type semiconductor and the positive terminal of the battery will be connected towards the N-type semiconductor. So holes get attracted to the negative terminal of the battery. You can see the animation over there. And the electrons get attracted towards the positive terminal of the battery as per the animation over there. So this result in the increase of the depletion region, the depletion layer or the space charge region, because you can see the repulsion of the electrons and the holes is happening against the space charge or the depletion layer. So what happens is that this result in the increase of the depletion layer as see in the animation. That's the depletion layer over there. Now the PN junction act as an insulator and will not allow any current to flow in the circuit. So this junction or this depletion layer now will be acting as an insulator and will not allow the flow of the electrons or holes in that region.
Okay, so this is
But in a
sufficient
particular
for you to
condition,
understand now. So did you get an idea what is PN junction diode now? All right. Any question? By watching this video, do you have any question in your mind?
No, it was clear.
Clear, right? So I have already shared that you can also watch it now. So this is all about now PN junction diode. So what is a PN junction diode? You know that how it is formed and you know how it looks like. These are some symbols. So this is it. So it has two terminals. One is P material made up of P material and another one is made up of N material. So P material terminal we call anode. This is called cathode. This is so when PN junction is basically a diode. So you know generally we call this is a diode, but technical name PN junction, which is a device that allows current only in one direction. So current can flow only in one direction. A few typical diodes are shown in this picture. We can see here. Also, now see, this is forward bias, girls. As I just show you the video, you can see. So this is P region, N region. This is the depletion layer, a potential barrier here. Yani it is asking you, give me some voltage, then I will permit you to flow the electrons across it. It's something like that. So we need to apply a battery here in a way so that current can flow in the circuit. Otherwise, no current will flow. So when we apply here at least 0.7 and more, current can pass. Otherwise, it's no. This is something forward bias. So forward bias, this is something for barrier potential in the depletion region must be overcome in order to external source. It cause current. For a silicon diode, it should be 0.7 volt and above. For germanium, it should be 0.3. The forward bias causes depletion region to be narrow. Now, this is the VI characteristics, which is also associated with your lab. So this is a circuit where we are connecting this diode, girls, and this diode will on and off depend upon this, the voltage here, which is forward bias. Why forward bias? Because we are connecting positive with the positive terminal, negative with the negative terminal here. All right. So once this is sufficiently given, so see, this is the VI characteristic. What is VI characteristic? Voltage and current characteristic. So here we have VF, yani forward voltage. So we are increasing voltage from 0 onward, current is not flowing. We increasing further, not flowing. Okay, like that. Up to here, not flowing. Just a minute, yes. So we still keep on, we are increasing the voltage, see, applied voltage, battery, but still no current. But when we reach to this particular, voltage barrier potential, which is 0.7, so what will happen? Current can flow through that. So this is something deterring. So the current can flow this way. Okay, this is the symbol of the diode, girls, So arrow is telling you how the current is flowing. This way current can flow, okay, only in one direction. This P type, this is made up of P material, this one is made up of N material. This is called anode, this one is called cathode. All right, any question here? Is it clear? This curve is also clear, how it is drawn?
Yes, clear.
All right. All right. So now this is forward bias. Now we will look for the reverse bias. This is reverse bias. So we just interchange the battery terminals, and what will happen? This depletion layer will become more widened. When it has become widened, so definitely it will behave like open circuit. It will not allow to flow of current. So now it is behaving like a switch. Whenever diode is in forward bias, it is behaving like a closed switch, and current can flow. And whenever it is in reverse bias, it is behaving like an open circuit, yani current can't flow. So this is something. So when a PN junction is reverse bias, voltage moves conduction band or something, and the diode effectively act as an insulator, relatively. But see what will happen when it is widened, but still there are some electrons which are very few. They manage to diffuse the junction, creating only a tiny reverse current, which is very tiny, which is in the range of microampere. They manage still, practically, but ideally we ignore it because it's very less. So reverse bias causes the depletion layer to be widened. See the this one now. So this is widened now, and this is here. And when we change the battery terminal, you can see positive, negative. So no current will flow. It will not behave. So there will be no current in the circuit. This is like that. So this is the reverse bias. So this one I already explained. This is for the forward bias characteristic. This is VF, forward voltage, IF, forward current. This is now a reverse voltage, reverse current. So ideally we ignore the minor current, which is because of very few. So what if we increasing the voltage, but no current is flowing, no current is, but very few, very tiny current can flow even if it is in reverse bias, which is in the range of microampere. But when we consider, we say, okay, it's behaving like ideally it is behaving like an open circuit and no current is flowing because it's so small or so tiny. That's why. So this is called VI characteristic of the PN junction diode. This is something. So this is a complete diode characteristic, okay, which we know this one. Okay, now, so when I was explaining you this, the previous slide, which is about reverse bias. So girls, we are increasing the reverse bias voltage. And you know what happened when we increase the reverse bias voltage? Depletion layer is becoming widened. Also, what happening? We are increasing reverse voltage. So those are electrons and holes inside. They are getting energy, but they are try to make the layer wider. But they have enough energy, and if we keep on increasing the reverse voltage, what will happen? Yani electrons will be getting too much energy. We are increasing voltage, still it is no conduction, but there is a limit how much reverse voltage I can increase. If I increase beyond that limit, electrons and holes will be having sufficient energy. They will come out from the junction, they will break the diode, and diode will damage at that time. So this is what we call breakdown voltage. Yani this is the maximum voltage, okay, after which diode will damage. Yani we cannot use it as a switch, yani on, off, it's finished. Now, I can give you an example of your gate, okay, gate yani you are maybe sitting in a room, you will be having a gate. This gate can open only in one direction, either inside or outside, that. So that gate can open only in one direction. Yani if you have only power to push this one, so maybe you can push inside and you can come to your room. But if someone try to push from inside to out, yani which is reverse bias, I am giving the example. So if you try to push it, will it open? No, definitely, because it can open only inside, right? Again, if we have two person to push it and again try it hard, still it will not open. Okay, we have now 10, 20 people, those are pushing in an opposite direction. What will happen? Ultimately, a time will come, the gate will not bear this much of energy and it will fall down. When it will fall down, yani there is no control, there is a not use of this gate in your room, like there is no role of the diode. It cannot work as a switch now, and on off, it will damage at that time. So this is what the breakdown voltage, yani this voltage will damage the diode and it will not behave like a switch later on. Otherwise, if we are using before this, simple, it will be working as a off switch, on switch, on switch, off switch, like that. So this is okay. And how would we know how much the breakdown voltage? So when you go to purchase the diode, okay, there is a data sheet for each and every diode. You can Google it for any diode data sheet. On that data sheet, you can find how much volt the rating is. So there will be mentioned, okay, this much is the reverse voltage. So we can apply that maximum. We cannot apply more than that. If we do, it will damage and circuit will, cannot reuse that one. So this is VI characteristic of the diode. Okay, and this is what a barrier potential 0.7, which it will consume. Now we'll discuss here. There's some models. This is breakdown. I told you this one. Now this is about the ideal diode. Okay, ideal yani we will say it is behaving like a perfect switch. Yani when it is in forward bias, it will work as a switch, close. Yani it will not consume any energy, khalas, and bus is like a switch, on. Now when it is in reverse bias, it will behave like a perfect open switch, yani close. So no current, full current, like that. So this is the ideal diode switch condition. So the ideal diode model is assume that it will conduct. As we connect, it will conduct. And even it is not consuming 0.5 volts inside this, to overcome this barrier potential. Another is practical diode. So practical diode, consider that the diode will not allow you to flow of current until you give some, what you call, give some, voltage to it. And it's like, it's here. In order to overcome this voltage, if it is made up of silicon, so I should give 0.7 volts, then only it will conduct. Otherwise, it will not. So this is the practical consideration. Yani, we will consider that there is a potential barrier inside the diode, and we should give at least 0.7 volts in order to remove or overcome that potential barrier. Then only it can behave like a diode, and it can behave like a switch. Similarly, for the reverse, okay, when it is in reverse bias, it will behave like a open switch. So this is a practical diode consideration. Okay, so if I ask you here calculate the current, so how you will calculate the current? I is equal to, you will say V bias minus VB over R. So this will be the total current. Okay, so you have to reduce this voltage from there. For example, if I apply here 5 volt and it is made up of silicon, so I will say 5 minus 0.75 over R. This is something. Then only, we can find the current. So it will reduce that one, and we will be having only 4.3 in my, circuit. So 0.7 is basically spent to overcome the potential barrier in the diode. Is it clear to all of you? Are you getting my point?
Yes, clear.
Clear?
Yes.
Okay, so this is about the practical, huh? Now, this is the complete model. So this is practical. What they said here, this is about the practical, huh? Model, and this is the complete model. So considering practical and ideal. So there will be a barrier potential. There will be a small forward resistance and switches there. And in complete model, we also consider this one. It is very small forward dynamic resistance. We consider a very small, because all electronic devices, whether it is of a simple wire, it has its own resistance. It gets heated. So this is very small. But in case of large, as we know that in reverse bias, there is a minor current flow because of some tiny electrons still manage to cross the junction. So here we have a very high resistance. That high resistance, it means a very minor current can flow. So because it's open, so they will try to go this way. So that causes a minor current which is showing here. So this is called a complete diode model here. So now it is all about the diode, and inshallah we'll continue next lecture. Here half wave rectifier and all later on, but not today. But see what I explained to you, whether it will conduct or not, some basic idea I can give it to you. Like here, if I just ask you, this is a diode, and I am connecting here, for example, 2 volts, and here I am connecting 0 volts. So will this diode in forward bias or in reverse bias? What do you think? Will it be in forward or reverse bias? Are you getting, girls?
Could you repeat?
The diode will be in forward bias or reverse bias now? This is P type, this is N type. Are you with me? Where are all? No one is talking. Can you hear me?
Yes,
Okay, so why everyone is silent? Okay, everyone is silent. Maybe everyone is watching video, which I share. What is that? I am asking here, will it be in forward bias? Okay, because this is P and N. Okay, forward bias, correct. Okay, now tell me what will happen now if this is 1 volt and here I connect 1 volt. This is anode, this is cathode. Okay, all right. No, I'm asking whether diode will conduct or not conduct. Conduct yani forward bias, not conduct yani reverse bias. Fai is watching video. See, she is smiling. Yani she's, yeah. So in this situation, what will happen if we connect 1 volt here and 1 volt there? You wanna see what will happen, or do you understand the point? You know, the concept is anode must be greater than cathode. Clear?
Yes.
How much it should be if it is made up of silicon? Yeah, reverse. Lena, correct. So how much it should be? It should always be greater than 0.7 for silicon. Correct?
Yes.
Then only it can conduct. Otherwise, it is in reverse bias. Like in this situation, when we are connecting 1 volt, so it is simply in reverse bias. There is no way it can be in, forward bias. Okay. So one more interesting fact here. 0 volt minus 1 volt.
It's going to be forward.
It's gonna be forward. Okay. Yeah. What about others? What do you think? Yeah, forward. Yes. So as long as this condition is true, plus it is gonna be in forward, because 0 volts is greater than -1. And how much it is greater? 0.7. So it is gonna be in forward bias. It is here basically relative voltage we have to check, Also, even we can have here -1 volt, -2 volts. Now tell me, what do you think? Forward or reverse? Yes, again forward. It is again because of?
Yeah, it's the condition that satisfies it.
Yeah, it is because of the anode is greater than this one. So it's very interesting concept actually to understand these things. So inshallah, the false state. In false state, we can check it, maybe just a minute. So for now it's okay. Inshallah, we'll continue later on. So first that I can show you at least this concept which I just explained to you. This is the first stat. Internet is not perfectly working. Some issues. You have class tomorrow or or today only?
No,
Yes,
we have class.
tomorrow we have.
One more class this week?
Yes.
Next week, huh? This week finish?
No.
Tomorrow is 11.
Okay.
We have one.
So you have lab tomorrow. Okay. So inshallah, Miss Mehash is taking your lab, right?
Yes, and we also have a lecture at 3.
You have tomorrow lecture. Yeah, one hour lecture tomorrow, right?
Yes.
Okay, yeah, that's okay, inshallah. So we'll be, going. See diode. I'm just showing you diode. This is diode. See, this is diode. Can you see it is conducting now? It's very fast. I think we can have a simulation speed. We can make it a little bit slow. Current, we can make it slow. See, current is conducting. Like here is what ground, and here is how much 0.7. Girls, if I just make it less, okay, just change it. Just double click here and change its value. Just make it how much? 0.5 volts. Let's see. No, it did not change actually. How to change it? Maybe stop it. Okay. Oh, this is slider actually. Oh, very good. All right. Let's see now. So there is a slider. It's a variable, right? Now I'm reducing the voltage. See, can you see? It's still conducting? Because 0 and 0.7.4 is still conducting. See, now it's still conducting, huh? Now see, when we go there further, maybe it will consider up to some point, then it will stop. Now is it conducting now? See, 0.7, exactly 0.7, should be a little bit greater, but now when you go down, and you will see like something. See, 0.6. Okay, but it is made up of which diode? Let me check the characteristic of this diode. It is made up of default model germanium. Okay, purpose. Yeah, this one. See. All right. So now, can you see the current? Almost very small because it's still 0.6. But if you go down, see, no current will flow simply this time. So it's 0.6, maybe a little bit current will flow. But if you go further, so no current will flow. Even if I increase the speed of the current, so you can see my minor current. Okay, let's see one thing now. Change this voltage rather than earth. We change it to any other signal. Like we have this voltage, current connected here. 1 minute. A draw wire is needed. I connect a wire here. Now, so now here we have 0.5 volt. Here we have 0.4. See the current. Any current flow? Stop. Right. This is something, and you can play here and you can see this concept here. Maybe I'll continue that. Okay, I'll tell you later. First for today's end, just stop. Okay. All right.
Okay, thank you, doctor.
Okay.
Okay. Tomorrow, inshallah, we'll continue. All right. Bye-bye.